All right, team. Okay, so 5 more lectures. Not that anyone's counting. So, okay, so I have this scaling stuff to finish, and this kind of crazy story I've been telling you. There's some more madness to go in here, and it's a great. I don't know. So it's still unfolding, but it's a great kind of history of science problem story, I should say, and. I really, it's a painful thing to talk about, but I'll show you the madness. Okay. Scaling, metabolism, river networks, very small differences between theories, Okay. What else? Okay. So all right. So this is a book that I ordered the other day. I had it before from. I don't know if you can see this. You can't see it at all. I'm trying to get this thing to work. So this is the energy metabolism book. It's from 1965. So it was a conference. So you see energy metabolism of cows in gestation and lactation. It's pretty practical. Comparative slaughter techniques. Stuff about sheep, poultry. This is pretty. We're trying to sort it out, right? Respiration and calorimetric. How to do it. Evaluation of feeds, the sources of energy. How much is in your hay? Final proceeding. So there's this thing at the end where they have this discussion, and it's all there actually. So, it's actually the people's names and what they said, and this ending thing, right? The proposal was then made formally by Kleiber and Flatt that weight raised to 3/4 of power should be used as a reference base in comparing the metabolism of different species of animal. The proposal was seconded by Dr. Mount and was carried by a vote, 29 being in favor and nobody against. It's kind of very interesting, and they're talking about, maybe it's a good sort of background thing to have. And I don't want to use it if I'm just talking about chickens within chickens. There's this funny little thing here. I remember this. This is why is surface area supposed to be differently related to metabolic rate? If one has to introduce surface area, we can still introduce the exponent 3/4 by saying that metabolic rate is inversely proportional to the square of the surface area. This is pretty great. A 1 over s squared is proportional to 1 over, so there should be mass to the 2/3 squared, which gives you a 4/3. But look at what happened here. Can you see this? Maybe you can't see this. Let me show you. So it's 1 over s squared, and they're going to say that is proportional to 1 over mass to the 2/3 because that's reasonable. And then, so this is squared. So this is 1 over mass to the 4/3, and then that this is equal to mass to the 3/4. That's what happened. Spot the error? It's true. This is just this thing. It's just sitting here, blah, blah, blah. And then Kleiber, and I don't know how he did it, but he just might have said, well, the fact remains that, just sort of moves on to the next piece. So I remember seeing that and thinking, wow, that's... Anyway, they typed it out, and yeah, not so good. Okay. All right, so let's get to the fun. And it's going to be earlier theories. And I think my little gadget doesn't work anymore. All right, so we had this crazy thing. The 3/4 would appear if biology was somehow 4-dimensional. Okay? There's this story that comes after it, which is getting a little more grounded. So it's elastic similarity, the idea that animals have allometric scaling as you go up through shapes. Maybe it's true for trees. Maybe it's true for some parts of organisms. It's never quite connected, and that's actually a very interesting thing to think about. And I talked about the other day that if you have something that scales allometrically, say in 3 dimensions, and it's something that is not a sphere but becoming more like a pancake, then it's more like a lower dimensional object, and that turns out to mean it has a lower exponent. Anyway, that's another story. And then we get to this. Okay, so this is what we'll talk about to start with. 1997, I think I said this, right? There were 9 reviewers for this, appeared in Science, very controversial paper off the bat, lots of fighting. It's a difficult paper to read through. I don't know, it's been cited at least 1,000 times. It's very significant in this whole business because it's the first time that anyone has ever figured out a story for 3/4 that's not completely mad. And it turns out it is, but it's just much harder to see that. So there goes our squirrel. All right. So here's the idea, right? We have these, just to refresh, we have these nutrient delivering systems in our bodies, right? For us, it's, for all mammals, it's these blood networks. You can think about there's other parts, such as the lungs, of course. We have that structure happening there, right? The bifurcation as you go down through the trachea, eventually ending up in the alveoli, and which apparently is quite different for birds, I think. I don't know much about it, but it's a different kind of story, right? It doesn't have that pure branching, which we do. There's an idea, a suggestion in this paper, it's not really explored properly, that plants obviously have a branching story, but here there's a sort of approximation that they're all a bunch of tubes, right? Which is not really true. It's a bunch of little cells that transportation moves through. Obviously, there's an overall network structure. So there's an assumption, and I'm not going to go through all the details here because it's impossible. I'm going to tell you the story. So here's the aorta, and we're getting to the capillaries here. This would be the idea of the way it's talked about is mainly the delivery part of the blood system, right? Rather than, so this is the arterial network, but of course there's a complementary venal network bringing the material back, the blood back. So the idea is there's some branching that's occurring, and in principle it could be quite general. It might actually vary, right, from level to level. But this is the aorta, and then you've got the next guys. And there are issues of the shape of the organism as to where things can be and all sorts of stuff. But basically this idea, which is well borne out, right? So, and I'll get to some data later on. If you do, and people have enjoyed themselves by dissecting various organisms and calculating these branching ratios, right? Okay, so we'll get to that. So each of these tubes here has some, so in general, there's an extra piece we could add, which is a little width of the a thickness of the tube boundary, right? Vessels, we're talking about vessels. So there's a flow, there's some speed of here it's blood flowing through here, there's some radius, and a typical length associated with each, right? So you'd imagine that these lengths are getting shorter as you go through these scales. There's a pressure drop across here, which gives you the movement. And the radii are getting smaller as well. But of course, there are more of them. Okay, so you're getting that balance. So the same thing happens with river networks, right? This is the outlet into the sea or whatever it is, and you have and it's of course structured in complicated ways, but you have this same kind of idea. So there was another, Da Vinci actually was the first person that I think it's sort of written down, noticed that, or talked about it. Of course, he was doing things with dead bodies that shouldn't have been doing. At least by, couldn't help himself. That's in the wrong spot. Wow. That's for another piece. Yes. All right, I'll fix that up. All right. So the assumptions are that the network is hierarchical, so no one disputes that. I'll put down, what the clear things are. Right? We do have some hierarchical delivery network. This is an important piece. So the capillaries are invariant across scale, right? So the capillaries or capillaries, whichever hurts you less, they're the same in whales as they are in mice, right? That's just a building block of mammals. There may be some variation, and people argue about that. Again, going in and measuring capillaries and difficult business, especially for the thing that's had the capillaries measured on. So, but of course you can take samples, not so bad. Hard to catch whales, right? Whales are a difficult business here. Sometimes you'll see them on plots, right? Because it's great to have the whale out there. That's a fantastic mass point, right? Why not? But it turns out they just kind of guessed where it should be, right? So I don't think, anyone's put a blue whale on a treadmill and stuck a VO2 max thing on the front. Completely different story for whales, right, as well, because they're living in fluid, and they have a massive amount of blubber. It's just a very different game for those guys. Brilliant things. And then this third piece, So impedance is minimized. The impedance of the network has been minimized as these organisms have grown up from little guys up to bigger guys running around under dinosaurs to bigger things, laughing about dinosaurs becoming extinct. So then we have this idea that yeah, sure. So that there's lots of different things that happen in natural selection. Lots of things are magnified, and lots of things are, right, you're trying to optimize lots of different pieces. But this is not unreasonable. You wouldn't want to have an ordinary network supplying like a really bad, silly one. So we'll get to that in other versions as well. But that seems reasonable, right? You need to be able to pump into this network. And so this is a good, it has great analogs with electrical circuits and so on, right? You're trying to push, right? You want the impedance to look as small as possible. So that's reasonable. And the output from this, so of course we get the that's what we're looking for, right? So we get the 3/4. That's the big deal. So this is this mystery solved story. Networks are fractal. So this is these delivery networks are fractal. And so this is actually, the math people love fractals, right? So you have a Mandelbrot set and fun, right? And you explore it. But there's no mechanism. There is a mathematical mechanism, but it's not really necessarily a physical mechanism as to where that comes from. So it's often not the case that you can describe these fractals all over the place, whatever it is, coastlines and so on. But the physical mechanism that gives rise to it can be tricky to get at. I mean, we have lots of different ones, but and we can connect them, details of the mechanism to the fractal dimension of the structure, whatever's being produced. But okay, a lot of them that we really enjoy are ones we just made up. Okay, pure mathematician. So quarter powers are everywhere, right? So this, and I had this connection a little bit before, right? So then you get things like the size of the aorta, radius as a function of overall size, things about the lungs, all these quarter power scalings. Connecting it to lifespan is much harder, given that it's all wrong anyway. But it's that's a tricky thing to get to. There is another body of work which I'll put in here eventually, but it's about so we do have good data on the growth of organisms, right? So how big they are is a function of their time on the Earth, and so you can average over those things, and you can think about, because obviously as you're growing, you're using energy in a different way. So you can think about where the 3/4 or 2/3 works there. So that's another business. Turns out it doesn't matter, but it's another science paper. Okay, so here's and I'm just going to talk through, because there's a whole bunch of math, and I don't want to crush you with that. So please understand, I'm trying to help. Okay, so Poisson flow and pulsatile flow. So Poisson flow, classic flow in a pipe, right? So this is, this is some old school fluid mechanics stuff. You have your pipe. You have a dynamic viscosity here, which so that's about the fluid itself. But the pipe has some radius, some length, and we'll just ignore this guy for a second. So some length and some radius, but essentially it's this story in here, the 8 mu pi over L over r to the 4. So that's the impedance of just a single tube. So this is a nice thing. So in fluid mechanics, you assume that the fluid right next to the boundary is not moving, right? The no slip condition. So the actual shape of the actual material, you're assuming, it could be lots of different things, but you're assuming that that's true to get to this result. You do need to know about the fluid itself, but essentially you end up with a parabolic velocity profile, right? So it's 0 at the outside, and then of course in the middle it's its fastest. So, right, the fluid has a viscosity, right? A thing that's it's impeding itself. So quite reasonable. You have a tube, you're trying to push stuff through it. The longer the tube is, the more resistive, okay? Totally exciting. And the bigger its radius, the less resistive, right? So you open it up. And that scales as so the details of these powers matter. So it's an r to the 4. So it's quick, right? So r squared is, of course, the area, cross-sectional area, but you're getting a real bonus for, a 10% increase, say, in the radius. It makes it much easier to get through, right? But that's linear in length, so that's quite reasonable. So that's a classic result. Now, what's the setup here? The setup here is that If you have, well, let me do it here. If you have, can I get it to work? Yeah, so if you have these tubes, right, so you've got all these tubes, so here's the aorta here, and you've got your ticker going bump, bump, right? And then it's going to break into a couple, and so on, and so on, and so on. So the idea is that these ones are in parallel. So it's just straight out of, you guys love electrical engineering, right? And this is, everyone does. And then this way it's series. Right? So if you stack up, so you can take out one section. So this is, say, the kth level. Yeah, this is good. Take out the kth level. It's all of these tubes in parallel. And what happens? So you have this impedance that's proportional to L to the K over R to the fourth. So we'll say ZK, the impedance at the kth level. Because they're in parallel, you end up with a 1 over N sub K, right? Sorry, that's R to the fourth with a K. N sub K of these guys. So they're in parallel. It makes it easier to get through. Fair enough? So that's a good thing. And in general, you have two guys in parallel. This is Z1 and Z2. And so Z total, 1 over that is 1 over Z1 plus 1 over Z2. Right, so if all these Z's are the same, we have N over Z, and we can flip it upside down, we get ZK over the 1 over N sub K here. Then they're in series, so you're simply summing them up. So this is an important way to think about this, actually, because, okay, so you're going to have bigger guys here, and then thinner, smaller ones here. So really, if you go through this properly, what you find out is you want however many of these guys, they just need in total to look like the level before and to look like the level before, right? So what I'm just going to say this. So you really find that the ZK equals a constant for optimal impedance. So it means it doesn't have to be fractal, right? It just means that every level has to look like the level before. So you're looking out here and you're pushing stuff through. You can't really tell where the levels are. So it's sort of a matching of impedance story. Exciting. Okay. Again, it's a Lagrange multiplier story, and I'm not going to punish you with that, but see, giving you things. What you want to do is minimize this quantity. And you have to estimate how many levels there are, and that's going to be based somewhat on the mass. Fair enough, right? It's going to grow logarithmically with mass. You have to think about that. But you want a bunch of constraints, and I'm not going to put them here, but the bunch of constraints will be the total volume of blood. So you don't want that thing to go up and down. We'll come to a very humorous problem with that later on. Volume of blood. There are some funny ones as well. There's some things about being, it's introduced in a bit of an odd way, but you want the network to be space filling. Fair enough. Which works for river networks usually reasonably well. Yeah, you got to get your, this is a complicated problem, right? So is the capillary density, not the capillaries are, we can think of them as being similar across all mammals, but the capillary density, how does that vary as you go across mammals? And so one idea is that, and it's just a hard thing to measure, one idea is that they become less dense as you get further up through organisms. And so this is this idea of elephants running at a lower rate, right? I'm not really sure about it. The other idea, of course, is just the cells have less mitochondria and there's just less stuff going in there. So there's some arguing and confusion about that. But basically, it is this big Lagrange multiplier thing. It turns out to work for Poisson flow, right? You have several other pieces out here. You differentiate with respect to N and L and R, and it will work okay. And what you'll find, however, is that metabolic rate scales as mass to the 1. There's a logarithmic correction, but basically mass to the 1. which is not the right story, right? So that's the kind of result we expect for maximum power output. Oh, well played. Gosh. And I thought you were going to, yeah. Good man. Danforth. Thanks, Danforth. All right, so I'll show him that later. Okay, so I can't do anymore. All right, so let's see. So, okay, good. So you get mass to the 1. You get mass to the 1 with a logarithmic correction, and that is what we expect for organisms when they're running as fast as they can. Okay, which for me at the moment is about 2 miles an hour. So, great. That's not right, but it's in the paper, right? So this is the thing. It's in the paper because it works, and it's something you can reproduce, and it sort of takes up the first third, and it's sort of illustrative. Then there's a point where they say, well, but that's not really how it works because that's the wrong result. And blood flow in organisms is not just exactly like flow through tubes. There's some more, right? So this assumes rigid tubes. There's work from the 60s by Womersley that shows that if you have flexible tubes, which is of course what we have, then and you have a pulsatile flow, then it's a different kind of impedance. So it makes sense. This is a horrible fluid mechanics problem. And clever fluid mechanics people sit down and solve things. And they right, and suffer through it, and then tell you should do that because it's the only thing to do. Anyway, so this impedance is very different. So again, there's this structure which this part and this part are about the tubes being in vessels being in parallel and then in series. That's the same structure as up here. This piece in here is the pulsatile flow impedance. And it's funny. So first of all, length isn't here anymore. So the tube gets longer. You don't see it. You don't notice that length getting longer, which is very weird, right? You're trying to push stuff into a tube. Someone makes it longer and it doesn't affect your experience of impedance as the pusher of things into the tube, the tick out. There's an out of the 5 halves on the bottom, which is less than what we had before, so it's 2.5. And now the wall thickness is in here. So makes sense that it might appear, but it appears up the top. So this is a different game altogether. And there are half powers. It's very exciting. There's a 5. If you look at this guy, if you play around with it, there's a sort of, so now you have to differentiate with respect to H and R and so on. There's a finding that you get these two to be proportional to each other, so this effectively becomes 1 over R squared. However, there's no two ways around it. You have to differentiate with respect to now these 3 pieces here. There's no reasonable solution, right? It mathematically falls apart. You get disagreeing. It's not that it's not ill-posed. I don't think it's ill-posed. You just simply, if you set up a Lagrange multiplier, you do not get a minimum. It just does not work out. Whereas this one, everything very nicely works together. You get 3 equations, and one of them has to depend on the others, which is true. Here you get 3 equations for which it doesn't work out, right? So in linear algebra, there's no solution, if you like, to this 3x3 matrix story. This is hard to see because it's not in the paper, right? It's very hard to see, and it was not really in the author's heads, as became clear because we told them about it, and they went and did some more calculations, and then they said, okay. Sort of said, okay. You can assume, and I'll get to this, you can assume some other things. You don't have to, let's just, this was nice, but let's do some other things. All right, okay. So this was the glorious, because this is, now we're doing science and math and physics, and you biologists might understand it, but stand back, it's okay. All right. Trouble is, it really doesn't hold together. So the paper we produced in the end was mostly about, the front of it was all about the data, saying, oh my God, people, what are you doing? And we put in that, and we said, all right, and also the theory doesn't work. We're trying to be very polite because it's a tricky thing to do. And we put a lot of that in the appendices, but it's just hard to, you got to work through it. So this is my, I'm not going to go through it all here. I'll probably have to do that in hell repeatedly or something. So why waste my time now? So, clearly going to hell. So it doesn't follow from the pulsatile flow thing. Just falls to pieces. And it doesn't, and in either case, you don't get this through the networks are fractal. You do get this rather very nice result that the impedance of the whole level has to be the same as you go through. So the scaling could be, there are twice as many little tubes at the next, and then 4, and then maybe 3. It doesn't matter as long as the widths and the numbers all balance out to give you the same number as you go through. So really you need this guy, LK over RK to the 4th n sub k. This has to be a constant. This makes sense. Now this is for the Poisson flow one because that actually works. You do get this. This is very nice. This is again for the Poisson flow. So the Poisson flow one does seem to apply for the outer branches, right? So when your blood starts to slow down, which is super cool, right? But this has been found from simpler optimality arguments. You have Murray. I think it's in. Let me try to think. No, it's definitely in some other work as well. But this is well borne out. It's true for plants as well and trees, right? So that if you have, and this is just super cool. This is a good thing to know. Murray's Law fans out there? Maybe? No? Never heard of it? Cool. All right, so this is really a fun thing. So yeah, you have your tube, nice tube. And which you've carefully removed from some unsuspecting organism. How you live with yourself. All right, so then there's an R1 here and an R2 here. There's really no reason that I need to do this, but I am. And then there's a R0 here. And this is pretty cool. So R cubed equals R1 cubed plus R2 cubed. And so this is well observed in organisms, in plants, as I said. There's a paper recently, maybe the last 5-6 years in Nature about plants. Someone's gone out and measured tons of plants. Well, when I say someone, I mean graduate students were forced to do it. And as is the way in those kinds of areas. No, I think they were on the paper, right? The old way was to get all the graduate students to do it and then acknowledge them on the 7th page in a footnote. Yeah. And thank you to Smithers, who died falling out of a tree. Did some excellent work before that. That's how you communicate it to his parents. All right, so anyway. So we've kind of moved beyond that a little bit, hopefully in some areas. It's true, like in sociology, if you weren't just a sole author on everything, then how we know that you're actually a scientist? It's just really bad. Very 19th century. So this is pretty spectacular, but there are simpler arguments for getting that, and it's just sort of a impedance matching type things and minimizing and so on. And then you can think about angles as well. That's another cool problem, like what's the optimal branching thing. Lots of fun things. So that does pop out. And I have this story about impedance being distributed evenly. You can still say, all right, networks are fractal. We know that. Right, they're kind of obviously, maybe we can get another thing. So there's a whole angiogenesis story here, right? So that's how do blood networks form? And so if you think about it, it's kind of tricky, right? So you have your little baby growing, and you have to have, all the while it's growing, this is a heart, and then you have to have the distribution network, and it has to loop back. So that has to somehow just keep moving out, right? So there's all these little nucleations that have to happen, and tricky thing. So how does it start off? That's a whole other problem. But the ontogeny of blood networks, yeah, cool. Okay, so we could assume they're fractal. We can do that. As I said, data backs that up. We'll get to that. And then we do this. So this is very much like the river network story. I've given them slightly different ratio numbers that appeared in the original paper, which I think I have one that's got my scribblings all over it that I scanned in. I don't know if that's the one that this links to if you connect. But anyway, so the ratio of the number of vessels at the kth level to the k plus 1th level to the kth level number. So that's a number. This is a number that's going to go up. So this ratio is greater than 1. These two ratios are less than 1 because the radius and the lengths are decreasing. As we go out, that's fine. It's fine, just the way they are. But at least they're ordered properly. And you do the kind of the opposite thing when you come to, traditionally, with the opposite thing's been done with river networks. It's called Horton-Strahler stream ordering. You start with the little guys and then you move in, right, to the big one. This is a reasonable thing when you start with the A order and move out. All right. So we could do this. We're going to assume that it's fractal, and then so these quantities here are independent of K, right? It's the same ratio all the way through. So if you do that, and this is the kind of conversations we've had with these guys. It's like, okay, just let's assume fractal. Then you do get this finding that the number of capillaries, right? So you've got a network, and you can estimate then the number of capillaries at the end of it, right? How many? You've got so many branching ratio, so many levels, and then at the end you've got a number of capillaries. And so then you say, and this is a bit tricky too, but you say, all right, well this is, you know, they're the little energy sources at the end, right? They're the fuel stations, right? Where you go and pick up your gas, right? Kind of. And trying. And that's going to be how much energy is being put out per unit time. It's going to be proportional to these guys. Now, of course, it is tricky. These guys aren't always on, right? They kind of go off. Parts of your muscles will go to sleep a little bit now and then, even if you're moving, right? But it's not bad. And if you do that, then you can. It's a bit tricky, but you can argue that because you've got a number of capillaries, this is tied to the network structure, and you're going to say it's proportional to basal metabolic rate. So therefore, if this thing is scaling with some power, then of course you have what this power of alpha is. There's some other pieces in there, but that's the story. So this is the connection. So alpha is minus, so it's log of Rn. So again, this was a number greater than 1, so this is going to be positive. And then log of the radius ratio appears as a square, and we have a length one here. So you can see this is kind of the volume ratio, right? Yep. And the way it's structured, though, is both of these numbers are less than 1. They've been flipped, right? It's the other way around. So this thing's less than 1. So this is a negative quantity. So okay. So it's a little bit of a funny business. There really should be log of 1 over that. But this is to match the paper. Yeah. There are some other issues about prefactors and things, but let's say, okay, fine, it's going to be fractal. We're going to throw in these things too. We're not going to derive them, we're just going to throw them in. We're going to say that you want area preservingness and space fillingness. And so they're slightly funny things. So the idea of this one is that as you go through these cross sections, can I do it? Good. So the total area, this is the kth level, and the k plus 1th level is smaller. So see if we can get this kind of lighter work. So we have nk, the total cross-sectional area here is proportional to the number of guys here times rk squared, right? So it's pi rk squared. And the idea, if this is going to be the same, even with constant, yeah, right. The pi doesn't matter. Okay, so there's going to be nk plus 1, and this will be rk plus 1 squared. So we get this, nk over nk plus 1. Let me write the other way. So it will be rk, I'm going to bring this guy over here, over rk plus 1, all of those guys squared. And this is nk plus 1 over nk. This is the thing we defined as r sub n. And this guy over here is the thing that we defined as 1 over r sub r squared. All right, so we get that piece. Then there's another idea that, okay, these are tubes, and we're going to say that they kind of fill space. So there are more of these little ones. This bit is kind of funny. I don't know. This bit is a little funny. So now we're going to say that nk times lk cubed is equal to, right, there's some constant proportionality, but they're going to be equal, nk plus 1 lk plus 1 cubed. And it's the same kind of structure as this, so you get that r 1 over r L cubed is equal to R sub n. So that is a bit of a funny thing. This is a way of getting space filling this. So the idea is you have a tube, but it services a whole ball around it. Yeah. It's a little bit funny, but the idea is that kind of the whole volume that is associated with each level is the same. And then the volume of our spherical cow, or whatever we're trying to make, has to be the sum of all of those volumes. So it's a bit funny. But you can't have the number of tubes kind of declines or gets too big, right? You can't have it exploding out, right? So that is that one is a little bit funny, but we're just going to assume those things, right? We're throwing everything away, and we're going to assume these pieces. Okay, good, we're soldiering on, right? Lots of bad things have happened, but we have just willfully ignored them. So let's see. So if we put this in, let's do it in our head. So we have a Rn minus a half. So we're going to put that there. So it's going to be Rn squared with a minus a half. So it's Rn to the minus 1. Delicious. And then we get a minus a third. So we're going to put that in. So we get minus 1 minus a third. That is minus 4 thirds. So this is Rn to the power of minus 4 thirds. We bring that out the front. We have minus 4 thirds. That is, we did the right thing. And then that and the minuses go away, and then we get 3/4. We didn't do what these guys did in their crazy discussion, right? That's okay. 3/4, and this is log Rn over log Rn. So magic. Super duper. Yeah, the space filling one is a funny one. Yeah. Anyway, that's how we get it, right? Totally excited. So, all right, so you have to throw away all the machinery that made everyone fearful and excited because you were physicists, and then get this sort of reasonable. It's kind of reasonable. It's not bad. It's not a disaster. Set up as a fractal. We have area preservingness, space fillingness. We have an argument here about capillaries connecting to, right, being proportional, the number of capillaries being proportional to your basal metabolic rate. Okay, maybe. And we get it. So one thing you'd think is very reasonable, the next thing you do is, okay, so so this is a brilliant idea really, right? So connecting the network to performance of an organism. And of course you can think about how that works for all sorts of systems, which we do. But you might want to go and look at the networks, right? So we did that, and we never published this, and I don't know why. I think we felt like we'd been rude enough. But it's gone on for so long that I don't know what to say anymore, because this is not, so this is a number of organisms that we dug out of the literature. So some of the individuals involved have been porcine in nature, and then, which is always a funny word, and then humans. Humans, some I believe were, offered themselves up to science, so it's kind of okay. This is another lead on a Da Vinci case. Rats, I think this paper, this is, as I recall, you fill the rat up with a kind of a nasty plastic, and then you remove the rat, and you have the whole network sitting there. Yeah. I mean, wow. Some of these other ones are, as you can see, so these are referring to arterial trees, and this is a pulmonary arterial, and so on. They're subsections, right? So you can get the scaling at least out of these things, right? You're not going to do the whole network. So yeah, you get it out and you start counting things, and it's a goopy mess. And you do some estimates and so on. There are some that are quite detailed, because it's not so this is a thing that comes up in the complex networks course. Real branching networks are not purely hierarchical. They're just not, right? So and that was a beautiful observation made by a Japanese researcher in the 60s, Tokunaga, and it's just a really beautiful piece of stuff where you see that there's still this really strong fractal story, but big big tubes have, or big vessels have vessels of all sizes coming off them. So they're called side streams or side branches. And the way that works has another beautiful scaling story. It works out that you still have this overall hierarchy, of course, but it's true for river networks and it's true for blood networks, right? So there are a couple of papers where people have done that. They've gone through and looked at these little side stream stories. So that makes it much harder to deal with, right? So we talked about this series impedance and parallel impedance. It's much, much harder to think about when you have all these little guys going off the edges. You can do something, but it's tricky. All right, so we have lots of guys in here. And so they've been estimates. This is just taken from the literature. Right? They're absent, of course, which is fine. This is the theory. It doesn't tell you what they are. It tells you what their ratios might be. So these are estimates, and these are somewhat hard things to estimate, but these are just, there's going to be some error on them. And so you see there's some consistency within organisms, right? So these are very consistent for our porcine friends, who are, spectacularly similar to us, right? We can trade organs and stuff. Actually, I guess it doesn't. Trading is kind of one way. Right, okay. Not so much a trade. Okay, right. We'll be in trouble for that. Cats, so we see this rat one again, which was a very detailed one, has a much lower branching ratio, which is Rn. There's some variation. I mean, it's not, there's definitely some variation when you look, and some similarity as you go through within species. And of course, these are just subnetworks of individuals, right? Colossal task to get a really big data story here. But you could, if you can make like this translucent brain thing, right? If you make humans translucent for a little while, give them some drugs and they're just translucent, and then you could take a picture of them. It's definitely something where an MRI that you can take with an iPhone would really help. Yeah. It's hard for trees, right? I mentioned this the other day. It's hard for trees, right? You have to run up a tree and count it, or you cut it down and then you chop it all up into little bits and see how old it was and comment on that as you've killed it. All right, so we can find these pieces. So this, by the theory, if this is the ratio for comparing the ratio for area and number, and this should come out to be a half, right? And it's the area preserving story. This is the space filling story. So just the way we've structured it there should retrieve that exact power, right? So it should be that, number times area. So we flipped it up, so it should look at it, right. So you see 0.45, 0.41, so it's a little bit under here, 0.39. These are pretty good, matches up pretty well. So the area preservingness is not terrible. It's a little, if anything, it overestimates just in general. I mean, this is not sort of a thing that has a variation where they go above 0.5. For a third, so we're looking for 0.33. Again, the dog does a good job for us. Very different here, certainly. Humans, well played. And then this is a little off again, all right? So they're off in all sorts of directions. And then we have our alpha, which is this, where was alpha? This guy, right? So we can put all these guys together and we should get 3/4 if it's magic. Our magic story works. So Turcotte, actually, so there's a whole paper about this, using this side branching stuff, actually, kind of derives the whole story. Again, got a 0.79 for an unfortunate moggy. And we have, the rat one has a 0.73. We have a 0.9 for a dog. These are, the pigs, they're doing a good job here with the 0.6. So, and humans are up much higher. So they're really all over the place. And so this is a hard thing to, figure out. I think, my feeling about this is that fractal networks are great for delivering things, right? And you need that kind of impedance story to be minimized. But there are many solutions. And so you could imagine evolution producing, different kinds of fractal networks that basically do the same job, right? As long as there's a pretty big sweet spot. Just being fractal is good, right? So that's why we have these. These things are not the same, and these things are not the same. They're not really tight. Again, there's some errors in this, but it's not a resounding story. All right. But that's, I think, really the big thing there. Common thing. There's been a lot of media about this, right? Nova's had specials, all sorts of things. That's more about trees, I think. This is a great book. So Power, Sex, Suicide, Mitochondria and the Meaning of Life has a section on this. Did a very nice job when he gets into it because you're thinking, oh my God. But as so often happens in science, the apparently solid foundations of a field turn to rubble on closer inspection. So thank you, well done. But people are tenacious, so let's have a look at this. There's I mentioned this the other day. So we get some people going back and forth about this, but here's a whole issue devoted to the theory, to metabolic rate of functional ecology in 2004. So these characters put their hands up and said, is this WBE model of allometric scaling mathematically correct and biologically relevant? Which was a bit dangerous to ask that question. And then yes, so they got to reply, yes, it is both mathematically correct and biologically relevant. And the truth is, two of them have no idea whether it's mathematically correct. I don't think they can do it. And one of them knows it's wrong. So it's a problem. Or maybe it's just completely confused. I don't know. So it's really a mess. So then 2005, this is the WBA's model of, again, the same questions remain. So they're trying to build the whole Simon and Mandelbrot thing, but I think that it peters out. These guys tend to, there's a bit of yelling that goes on, sort of, taking tips out of Congress or actually Parliament from the UK. All right, so it's a mess. It's a total mess. And so before all of those journals sort of lit up with discussions about it and everyone being confused and so on, there was another work, and I want to tell you about this one. So this is Bonava, Maritain, and Ronaldo appeared in Nature in '99. In '98, I think, must have been '98, my advisor and I ran a seminar on physical networks, right? So it was physical networks, we were reading about all these things. And so the first paper, we knew we were in trouble, this is a mess, this thing. So the first couple of weeks were devoted to me talking about this West, Brown, and Enquist work. And in the audience was this guy, Andrea Ronaldo, who's a terrific character. He's from Italy, lives in Venice, and he's at the University of Padua, I think. Played rugby for Italy back in the day. He's a really very lovely fellow, good fellow. And so he's sitting there, and he was visiting MIT for a year. So he's having a great time because he's a river networks specialist, right? So he's done a lot of things, but one of his things is hydrology in general, but one of his things has been river networks. And so he had this big work on optimal river networks sort of story, optimal channel networks. Anyway, they're sitting there thinking, well, look, networks, this just is describing this, it's solving this great problem in biology, but we know there are problems with it. Let's have, we have a better story. And this is a really hard one to fathom, I have to say. So they come up with this, and so here's a simple point, right? So there's a source in all of these cases, and then you have some area you're trying to supply. So here we have our two-dimensional organism, if you like, and we have a heart in the middle, and there's just trying to get stuff out, okay? So it's a constant supply, and the idea is, you see these numbers in here, the idea is that there's some flow coming through here, and this is, in a sense, a little area that's being supplied locally. So you can imagine there's capillaries kind of coming off here. The amount of fluid that needs to come through here to supply all of these guys, well, you need one sort of unit, one sort of amount of stuff per unit time for everything to survive. So you imagine the tubes are getting thinner. The tube here says 1, 2, 3, 4, 5, 6. So what's coming out here has 6 units per time, so it's thicker, right? One unit gets drained off here, then there's going to be it's going to have a thickness of 5. Another one gets drained off here. Maybe I've miscounted. And then 2, this will have a thickness of 2. 1, there's like a little pipe coming off here, and there'll be 1 down here, and it'll supply that area. 2 again in this direction. Does that make sense? It's a reasonable thing to say. Yeah, not bad. So this is a terrible way to supply that, right? So because your network is very long, and it has to be very thick in the middle, this is going to be bad. So this is sort of the story. You could have loops in there. There's some very nice work on this too, whether you have the transition between a purely branching network to one that has loops. because leaves, for example, have loops, right? So there's good resiliency in those things. You can cut out a piece of a leaf, like this kind of what looks like the aorta, but it'll still function. You know, you're a very bad person for doing it, but you can do that, and it's okay. And I've talked about this. I mean, we have, you know, it's not purely hierarchical for people or for organisms, right? We have the circle of Willis. Went pop. Oh. Come on, thing. Quality. Can anyone explain what's happening to me? Is it too hot? What's going on? It just choked to death. Is that what it's doing, do you think? All right.
I don't think that's what it's doing. I think it's turning its fan on, so it's maybe either should we vault turning it on and off is typically the first step.
It's got off flashing tremendously. Come on, I know you're off.
Might have to do a couple manual
Okay. It'll come. So let me see. Do we need to get up there and poke it with a stick?
The lamp light is running. I don't know if
What are we going to do? We're going to stand up there and, I mean, it's crap. Something's red,
the lamp light is red.
which is usually green. That's good. Yeah, there you go. All right. Thank you. All right. Excellent pushing of a button. Very good. Outstanding. Modern humans overcoming adversity. Can't talk without pictures. And the weasel is dead. All right. Okay. Thank you. Well played. All right. All right. So this is now. There's no impedance in this anymore. It's just a geometric argument. And I have to say, this took me about 10 years to kind of really fully understand. But it has some sneakiness in it, which I will try to explain. And in fact, I tried to explain this very much to Ronaldo in 1998. And so, is that right? Maybe it was early 99. And you know, they had this preprint, and I'd read through it, and you know, it's all very collegial. And so I was a graduate student, so I was being very deferential, of course. But as I said, he did play rugby for Italy. But the guy, so no, really nice guy. And so I came over to his office and spent, I don't know, an hour and a half explaining why there's some really fundamental problems with this theory. And he said, okay. So he went off to meet with his colleagues, and he would come back and we'd talk again. So he came, I remember he came into with the green building, the one they played Tetris on. He came into the office, and I said, okay. And he said, it's just been accepted at Nature. So I'm like, okay, bad. Not a good time to talk. We did have a talk, but there was a lot of smiling, and yeah. Anyway, so It got accepted in Nature. So it got published, and it has this problem. There's a funny problem in it. Okay, so they find the most efficient network has this in d dimensions. So this is pretty groovy, right? So d over d plus 1. So we're in 3 dimensions. We get our Bloom story, right? We get there's some sort of 4th dimensional story. Okay, they get that. So we're going to get 3/4 because we're going to put d equals 3 in there and celebrate. We've also solved arbitrarily large dimensional organism problems. But they also find this, and this is very clear as they go along, there's some weirdness in these supply areas, right? So this idea that and you saw this on this picture, that as you scale up in size of these things, that these centers get further and further apart, perhaps, or it's kind of unclear. And really the assumption is in their paper that they actually stay kind of on a grid, so they don't spread apart. It's a big deal. They also find this, the volume of the network, right? The blood is in the network, scales as mass to d plus 1 over d. So when d is 3, we get 4/3. So it's scaling superlinearly. The volume of the network in the body, which is scaling as mass or volume, right? It's v. So that's bad. So if you can do a simple calculation. So if you have a 3-gram shrew and its volume of blood is 10% of its body, let's say. Okay. It's not 150%, it's 10%, it's some fraction. So you could scale that up, and we get our 3,000 kilogram or 3 million gram. Elephant is going to have 10 times its body. It's going to be involved in the blood system. That's just in there. It's in there. I mean, I'm not making this up. That's in there. So that's going to be bad, right? It's not going to work out. And it's kind of like the bumblebees, can't fly because fluid mechanics says they can't. It's not like you come up with your theory and they all fall out of the sky. Or elephants say, "You're right, I'm dead." So they have a paper that appears in PNAS a couple of years later that sort of says jokingly in the abstract, somewhere in the intro, yes, this would be kind of silly. Here's another variation on it, which is equally contorted, right? So it's this desperate efforts to get 3/4. This can happen if you really want your theory to produce what you really think is true. All right, so years and years of kind of wondering about this, and I'm going to give you a very simple geometric argument. This is a Physical Review Letters paper, and it's from a few years ago now. But it's correct in what it is, and nature can do whatever it wants, I suppose. But it does seem to, and it's from teaching this course and from other courses. Okay. So it's going to be inspired by the Banava thing and because it is so confusing trying to work through that stuff. But that is one of the upshots, which is not good. Right, okay. But it is very confusing. So I'm just going to try to explain this well. So we have one source and many sinks, right? So you can have lots of problems you think about. Many sources and many sinks, which could be people moving around the country or boxes moving around the country, right? That sort of problem, that's a good problem. So that's a redistribution thing. This is more of a distribution or a supply, a collection kind of network problem. And there are there's really so many beautiful things associated with this, especially with the distributed sources and sinks, and that's another problem we'll get to. Well, maybe I'll do that. Okay, so we've got one source, right? We've got a ticker. We've got many sinks in this d-dimensional volume, and it lives in a big D-dimensional space. So that's important, right? So river networks are sort of living on a 2-dimensional thing, but there's a 3rd dimension, right? And this is the problem that I think Banava and so on ran into, right? We have 3-dimensional networks in a 3-dimensional body, so we can't do that kind of. The river can't get deeper. So there's a different scaling associated. There are different kinds of networks. So that's a big deal. So we're going to assume the sinks are invariant. That's it's a thing. You could say the sinks vary in funny ways, but let's do that. And there's some sink density. This is a really ridiculous, embarrassingly simple story, I suppose, but hopefully transparent. So there's going to be sink density, which itself could scale, right? So this is this problem I was alluding to. You know, maybe the capillaries get further and further apart as you go up through organisms. Maybe, right? I mean, why not? Okay, so we'll let that happen. And there has to be some reasonable cap on the, right, things can't go supersonic. All right. And this is similar to what I showed you with the Banavas story. So here's our very idealized looking hut, and we have flow out to 3 destinations. So there's a sort of a thickness of 3 here because this guy's absorbing 1, and there's an absorption of 1 here and so on, right? So you can break it into these 3 parallel networks. And so there's some issues with impedance, obviously, right? Because combining fluids together does a better job. But it's just a geometric story. We're just trying to figure out some minimal structure stories. So this is 3 pieces that make this little subnetwork. Okay, but if not worrying about impedance, but in terms of the volume of the network, well, now if you break it down to this picture, you have 1 pipe, you have a pipe of length 2 and a pipe of length 2 here, so you can add it up easily. So then it just simply depends on the distance you are from the source along the network. Okay. So here's the question. You need to have this be sustainable as you go up through size. So what's the best you can do for a number of sinks? Obviously, you can always supply 1 sink or whatever you want. So another way to phrase that is, what's the highest alpha you can get for the number of sinks as a function of volume to the alpha? So I guess we'll start this. All right, here's the picture that hopefully inspires you to greatness. All right, so we have some shape that's been, right, there's a family of shapes. They're maybe not exactly the same, but they're statistically similar in some way. And this is a 2D example, so there's 2 length scales. Somehow we have to orient an axis around it. It scales in one way, differently potentially to another. So this is one where there's kind of a stretching going along in this direction. So this family of objects is going to be in between a family of objects that are purely 2-dimensional and ones that are purely 1-dimensional because it's stretching out. So there's some volume V prime and some volume V associated here, and this omega is kind of the shape, right? And so there's some, there's a source in the middle and all these sinks outside. And in general, we have d dimensions, and we'll have the length scales, each length scale, so this is L1 and L2, each length scale has to scale as the overall volume to some power. And those powers have to add up, gamma 1, gamma 2, they have to add up to 1 because we're going to multiply all those guys together. And if it's isometric, then the gammas are all 1 over d, right? So it's going to be a third, third, a third if we're just in 3 dimensions. If we have funny shaped organisms, then they're going to move away from a third. And if it's allometric, right? It's allometric as long as one of these guys is different from the others. Okay. Funny way to say it. 2 of them are different. All right. Okay. Fine. Okay. Not a question for you guys. Don't worry about it. So, see, mercy, good. Okay. So we have spherical cows. So these are cows that are, right, there's a whole bunch of spherical cows. Yeah? We have to draw a spherical cow. Okay, so we have a spherical cow because that's what good physicists do, right? We have to have spots on our cow. And then we have, it looks like a chicken. So we have little ones, right? So we're going to scale these guys up. Yes. Or we could have ones that are more ellipsoid shaped. Maybe. So that's a basic question: is how does the surface area of these cows scale if it's if it grows isometrically or allometrically? And it turns out that has a beautiful connection then to this kind of optimal scaling thing. But I'm not going to punish you with that today, but I just wanted to have it up here. Yeah. Right. So in general, given we have some allometric scaling for the length scales, how is the surface area of these objects scaling with volume V. So you see if it's getting really, really thin, for example, right, then it's becoming kind of a one-dimensional object. It's not scaling as strongly as it could. Okay, that's fine. Right, this is Banavast's story, very simple, right? So the worst thing you could do is have your network wriggle all over the place before it gets to the destination, yeah? And very obviously you want it to go pretty much directly, all right? So the minimum network volume, given all these tubes, they're supplying sinks of the same size, so if you break all these tubes off into separate little pieces, they have to be all the same thickness. So it's going to be proportional essentially to the sum of all these distances from the sink to the sinks back to the source. So there'll be some network configuration, but you do the best you can to get that flow as directly out as possible. Very simple, right? That's the best you could do. Very, very simple. So there's some messing around with that you can do. This is actually the commuter rail and the T for Boston. It's work done by Gassner and Newman. Gassner has these two had a series of very nice papers on spatial networks. And this is using various ways of, say, actually trying to find them. There's the real one. Let's see. So this is the real one. This is a star graph. So if every destination, Braintree, and all these guys had their own train going directly there, MEFA, you get one straight up to there. Then this is a minimum spanning tree. So this is a bit of a funny thing to do, but it's there's only n-1 links in here connecting everything. So you subtract out links so it's still connected. And then they have a model that tries to find the minimum network, right? So there's a whole thing with slime mold. I don't know if you know about this one. So there's a paper that came out. And they put the stations of Tokyo, they laid them out as they are, and then let a slime mold grow on it. And it actually kind of reproduced the subway network of Tokyo. So it was a very nice piece of work. The point was that it grew a kind of an somewhat optimal network. And yeah. I think people just have slime mold sitting around, and there's really no defense apart from that. It's like, well, what can we do with it today? We've been breeding it for 30 years, and they do make all sorts of funny shapes and so on, but yeah, that's what happened. So look, good evidence that this is true. I mean, this is the real one. This is a kind of an optimal one, if you like. This is obviously incredibly inefficient, but in terms of the actual distance on the real network, compared to the star one, it's not that bad. So I'll just give you this, and we'll come back to some of this on Thursday. But so the minimum volume network, you have to integrate it over the volume, and it's simply what's the density of sinks at a particular point in space times the distance from the center. So you put the origin at where the heart is. This is not, you don't have to do this. We're not going to do this. You can fiddle around with this thing, right? So there's going to be this is just a Pythagorean formula for distance. So there's going to be an x1 squared plus x2 squared up to x little d squared with a square root on top. You take I'll just talk you through it. So what happens is you take the dimensions that are scaling fastest, right? So you could have two dimensions that are scaling fast and one scaling slow in, say, 3 dimensions. But in principle, there are k, and maybe there's only one that's dominating. So as this thing gets bigger, you see those dimensions win out, and they become the dominant story, right? So if we have our pancake cow, right, then this dimension doesn't matter. It doesn't really feature eventually, right? It's just these 2 dimensions here that are giving you all the stuff. So this turns out to be, what you do is right, you just do a transformation of variables. So we start with x, we go back to this u here, such that now we're just integrating over the basic shape itself, which has a unit size, a unit volume. So this integral is just some number. It doesn't scale anymore. And in doing these transformations, this pops out the front. The rho is just, we're assuming a constant as a function of the volume. Sorry, for a given shape, it has some value. It may scale with overall volume. It's a constant throughout the region. We get volume 1 plus gamma max, so the maximum exponent pops out the front. How do we feel about that? Magic happens, okay. It's not too bad. And you can do some simple examples with square shapes and so on and compute things exactly, but that's fun. Okay, so this thing is just some number. The dominant stuff is coming out here. So this is the volume of the network. So you can see what could happen here, right? So this gamma max is a bit of a problem. So if we're talking about the volume of the network, we get a Banavar problem here. This is volume to the 1 plus something, right? So that's going to be bad news if this is, right? We're going to have that whole trailer thing out the back, and nothing's going to work. Whoops. So this all goes away, and this is our story. But what can happen is the density of the sinks can change, all right? So we'll come back on Thursday, and we'll look at what happens when we apply this result to blood networks and river networks. And it's all goodness. It's all goodness. No more lies, people. If the cabal doesn't get me.